Welcome to Study Loop.
Hello everyone, today we're doing chapter 14, problem 10, and this problem asks us, given the H&MR spectrum of these compounds, which of these H&MR spectrums will give a ratio of 2 to 3? So which one of these compounds here would give an H&MR spectra ratio of 2 to 3? So this refers to the integration of your protons. So what you need to do in order to determine your ratio of your chemically unique protons is first to identify how many chemically unique protons you have and how many protons are involved in those unique protons. So let's start with the first one. You see we have a CH2 here, a CH3 here. Well, we know that right off the bat we have two chemically distinct protons. Why? Because this CH2 is directly bounded to electronegative chlorine, while this CH3 is one carbon away from your electronegative chlorine. And there's no chiral center, so we know there's an internal plane of symmetry. So there would be two unique chemically distinct protons here. So now we know that we have two unique protons. One of them has 3 protons, while the other has 2 protons. So now we have a 3 to 2 ratio, or you can say a 2 to 3 ratio. So yes, this one does create an NMR spectra that would have a proton ratio of 3 to 2 or 2 to 3. So now let's look at this central compound here. So this compound, once again, identifying how many unique protons there are and how many protons are involved in each unique set of protons, we see that we have an internal plane of symmetry here. So this internal plane of symmetry tells us a few things. It tells us that what happens on the left is the same that's going to happen on the right. So we know that these terminal 3 proton is unique from this single proton up here, but because we determined this on the right side, we know the left side must be true as well. These 3 protons are going to be the same identity as the right proton. So these 6 protons generate one unique type of proton. Then we have these 2 protons here, which are identical to one another. So now we have a 6 to 2 ratio, which reduces down to 3 to 1. And a 3 to 1 ratio is not a 2 to 3 ratio, so this is no. We do not get a 3 to 2 ratio in this example. Now if we look at the next example, once again, we have an internal plane of symmetry. And if we identify the protons, we see that we have CH2s on each side and CH3s on each side. So once again, what happens on the left must be true for the right. So if on the right side I have 2 unique chemically distinct protons, then on the left side, these 2 protons must be identical, and these 3 must be identical to the right side. So in essence, even though we have 2 different protons circled here, because of the internal plane of symmetry, these mirror each other, not only in terms of how they look, but in terms of their chemical environment. So they exist in the same chemical environment as each other. So these 6 protons make up one unique proton group, and these 4 protons make the second unique proton group. And when that reduces down, we get a 3 to 2 ratio. So this is, yes, we do maintain that 3 to 2 ratio the question is asking for. Now what about this? So this is a little harder to identify the internal plane of symmetry, but it is doable. If we cut across the sigma bond right here, we see that the left side matches the right side. So once again, if we draw out the protons off the carbons, we know that what happens on the left must be true for the right. So we know that the terminal proton is unique from this proton group because these 3 protons off this carbon is directly bounded to an oxygen, while these 2 protons bounded to this carbon is bounded to one oxygen and one carbon on the other side of this internal plane of symmetry. So we know that these are going to be 2 unique chemically distinct proton groups, but we know that what happens on one side must be true on the other. So we know that these 2 protons must be the same as the other two on the other side of internal plane of symmetry, and these three must be the same from one another. So once again, we have a 6-to-4 ratio of proton, which reduces down to 3-to-2. So yes, we do have that 3-to-2 ratio the question is asking for.